Anya, thank you so much for joining us. Here we go. There we go. We can see you. It's an absolute pleasure to have you here. And Anya, you're going to be talking a bit about the introduction to machine learning and an overview of popular algorithms. We are bang on time, so I don't want to take any more of your time than I need to. But Ananya, please take it away.
Yeah, sure. Let me just share my screen.
No probs. And do introduce yourself, because we'd love to hear more a little bit about you as well.
Yeah, sure. I'll do that.
We can. There we go.
Yeah. Do you see the presentation, right?
We do.
All right. Okay. So hello, everybody. I'm Ananya Vedala, a Gold Microsoft Learn Student Ambassador, and also the co-founder of Girls Code. And I'm here today to talk to you guys about popular machine learning algorithms. And in case you guys want to reach out to me and you have any sort of questions, you can reach out to me on LinkedIn. And so this talk is just about an overview of the famous machine learning algorithms that you would need to kind of start off in the path of machine learning and AI. So let's dive right into it without further ado. So we have three types of machine learning algorithms. They've come under three buckets. The first one is supervised learning, the next is unsupervised, and then there's reinforcement learning. So under supervised learning, these models, we're basically guiding these models. So you're giving inputs to these models as well as outputs and telling them that if these are the inputs that you get, this is how the outputs are going to be. And that's how your model is trained. And when you get new inputs, depending on how you've trained your model based on the previous outputs, you get new outputs. That's about supervised learning. Coming to unsupervised learning, you're not really guiding the model. You're just giving the model inputs and asking the model to come up with patterns or clusters or whatever it can with that given data. So not really guiding it. That's unsupervised learning. And reinforcement learning, on the other hand, is a little different from supervised and unsupervised learning. Here, the models are interacting with the environment. So they get feedback directly from the environment. Say it could be rewards or errors. So let's take an example of a self-driving car, like we just listened of, right? So in case your car, for example, it has to take a right, but it decides that it's to take a left. That's when it gets an error from that. It gets an error and it's kind of redirected and it's told that you've got to go right. And when it's decided to go right, it gets a reward. And that's the path it takes. That's how reinforcement works. It's completely different from your basic supervised or unsupervised learning. Now, moving on to the first supervised learning algorithm that I want to talk to you about. This is the most basic algorithm that you will ever come across. So as we see on the screen, it's basically a linear model. It's a model that assumes a relationship between the input variables and a single output variable. So here your output variable is the dependent variable, and your input variables are all independent variables. Let's just take the picture on the left bottom. So over here, we're trying to find the relationship between the income a person gets and the happiness score. So out of common sense, if you think about it, the higher your income, the happier you are. So that's how the line is drawn. But how does the model figure this out? There's something called the least squares error that the model follows. So what it does, it finds the error between your predicted value and your actual value, and it tries to minimize it. So it's just basically trying to get you the best possible line, minimizing the error. And this can be done with just one variable or multiple variables as well. So over here, we just have one variable, right? So it's called simple linear regression. Now, if you have to consider multiple variables, like if you think about the second point right there, we're trying to figure out how temperature is dependent on solar radiation, ozone, and wind. But you also see W1, W2, W2 and W3 there. But what are they? They're basically the weights given to each of these coefficients. So it's just, you're just telling, with the help of these weights, you're trying to figure out how exactly that input variable is dependent on that output variable is dependent on that specific input variable. So say, let's just hypothetically take an example that your solar radiation creates a huge impact on the temperature. However, on the other hand, wind does not really create that much of an impact. Again, it's a hypothetical situation. So there we see that W1 ends up taking a higher value and W3 automatically takes a lower value. So these are the coefficients that you get. And when you get these coefficients, you try and minimize the error. The model does it automatically. So that's the case of linear regression. You're just trying to figure out a linear relationship between your input variables and your output variables with the help of coefficients. And the picture on the bottom right, that's the formula of error, and that's what you're trying to minimize at the end of the day. Coming to your logistic regression. Now we've spoken about linear regression, but what if now these outputs are just zeros or ones, and you just want to figure out the probability that a specific input, let's say in this case, is either a dog or not a dog. You're just trying to figure out if it is or it's not, and you can't really use linear regression there, right? So say if you want to try and come up with use the least squares error in this case, some people would argue that the best fit line would probably be somewhere in the center wherein the error is minimized. Some people would argue that in case your data set that you've taken is not balanced. So when I say balanced data set, what I mean is that your inputs, half of them are dogs and half of them are not dogs. So say your data set is not balanced and you have more dogs and less cats. And you might argue that the line that you draw should be near, like it should be on the points that say that all the points are dogs, right? That you would say would reduce the error, but that's not how it works. In such situations, what we do is we use something called a sigmoid function. The formula for sigmoid function is given right there. S of x is equal to 1 by 1 plus e power minus x. This, in layman terms, it packs all your values in the margin of 0 to 1. That's what sigmoid function does. So at the end of the day, you can use sigmoid logistic regression for both classification as well as regression. So in case you want to use it for classification, there's something called a threshold value. So any sort of probability that you get above the threshold value. Say hypothetically your threshold value is 0.5 and you get an output of 0.7. So automatically you classify that into the category of 1. So in this case, category of 1 would be it's a dog. So you can use it for classification that way. And in case of regression, you directly get the probability that a specific input is a dog, like the probability of that. And in order to get the perfect sigmoid function, we use something called the maximum likelihoods concept. That's a lot of math goes into that as well. I've provided a link here, and you can go there and read more about it. I will be adding all of the links to the resources page as well, and you can visit them if you want to know more about maximum likelihoods. Now coming to K-nearest neighbors. This simply uses the idea that points that are close to each other are similar. So let's take the example of the second image right here. So first of all, the value of k is an arbitrary value. If you want to know the right value of k that you have to take, I'll tell you why we're using the value of k in a bit. But if you have to figure out what's the right value, there's a lot of research that goes into it. You can read a lot about it. I will be putting in links for that as well. And if you want to read about, and there's also another way that you can find the best k, and that would be through cross-validation. Again, the link is here and you can read about it. Let's understand why this k is used in the first place. So the second image that we see here, let's take the example, let's take an arbitrary value of k as 5. Now we want to classify the star over there into either circles or rectangles. So if we've taken the value of k as 5, we take the closest 5 points to that star. So visually, when you see that the three circles that are extremely close to the star and 2 that are comparatively farther, right? So, and 2 rectangles is what I mean. So totally, when you look at the 5, the majority of these points are circles. So you automatically categorize your star into circles. So the closer points to the star belong to the circle category, and hence your star will automatically go into the circle category. Now look at your first image over here. Say you have to classify x epsilon into either omega 1 class, omega 2 class, or omega 3 class. Again, we take the value of k as 5 in this case as well. And we see that 4 of the 5 points that are closest to x epsilon belong to omega 1, and 1 belongs to omega 3, but none of the closest points belong to omega 2. Now, if you look at the majority of these 5 points, 4 of them belong to omega 1. So you automatically put x epsilon into omega 1. So that's how x epsilon is classified. This is how the K-nearest neighbors algorithm works. Also, I'm just giving you an overview of all of these algorithms. There's a lot of math that goes into it, but it's all on you how you learn it. And I'm just trying to provide a pathway so that so that you understand that this is how you start off with machine learning. Now coming to naive ways. So I will explain this naive Bayes to you with the help of an example. But before that, I'd like to tell you that naive Bayes, there's two types of this classifier. One is the Gaussian naive Bayes and the other one is the multinomial naive Bayes. I'll explain to you the multinomial naive Bayes right now. So say you've got a new mail and you want to divide it, and you want to either put it in your spam folder or your non-spam folder. And assume that all the mails that you have right now are equally divided. You have half of them into your spam folder and exactly half of them into your non-spam folder. So how this algorithm works is that, first of all, you make a very innocent guess. So that's where the word naive Bayes comes from. That's where it gets its name. So you take a very innocent guess. Say you have any random new mail that comes. As a layman, which if I had to ask you which category you would place that mail into, looking at your previous mails, you'd say there's 50% chance that I'd put it into my spam, and there's 50% chance that I'd just put it into my inbox, right? So that's the first step. That's your prior probability. Now, after that, say your mail just has two words, something like hello mother or hello friend or something like that. So let's just take an example of hello friend. All right, now what you have to look at is what is the probability that given you have a mail, the word friend goes into that specific mail. So say your mail is in your inbox. What's the probability that the word friend is in that specific mail? Now, given that the mail is in your inbox is the key right there. Now, if you look at it, if you think about it, the word mother or the word friend there's a high chance that it would be in your inbox rather than in your spam, right? So automatically the probability there would be higher. So when you multiply these probabilities, now this is done for every word, say it's done for every single word in your email, automatically the probability that that specific mail, now that we've taken a mail with just two words, the probability that it would be in inbox would be higher, since the word mother must, or the word friend must have a higher probability that it would be in the word in your inbox. So that value is compared. So if there's a higher probability that those two words go into your inbox, your mail gets classified into your inbox. And if there's a higher probability that it would have been in your spam, your mail gets classified into spam. This is a very this is an overview of how naive Bayes works. There's also Gaussian naive Bayes that you can read about. And in this case, we can use likelihoods and probability as interchangeable words, but otherwise likelihood is the word that's used in place of probability when you have discrete values, not continuous values. Now, coming to the applications, these are some of the applications that naive Bayes works on, and you can try and work on these as projects or just as practice, just to know more about naive Bayes. Now, coming to decision trees. So in this is an algorithm in which at every step you ask a question to the algorithm. Like the algorithm itself creates these questions, and it's asked. Like let's take this animal tree for instance. In the first step, it asks if the animal that comes has feathers and then can fly, and then that's how it categorizes. But the issue that we face is that just imagine that in the first step that we're trying to classify, the classification becomes extremely biased. So say 90% of your data goes into, say true, say that 90% of your data has feathers and just 10 does not. So automatically you've completely biased your data set, and you're not really being fair to both the sides, right? You want it to happen in such a way that your topmost classification is equally divided, so that at every step when you're dividing the data set, it's pretty much equally divided, so that you're not having any sort of bias when you're providing conditions. Because when you look at the example that I've given here, the question has fins and has can fly are not same. So you're providing different questions at different positions. So you're not really treating the whole data set as fair. So the whole idea behind decision trees, the whole challenge that comes with decision trees is that at every point, you have to make sure that your impurity is less. Now, when I say impurity, what I mean is that the division, in layman terms, when you're dividing your data set at a specific point, it has to be divided in such a way that both the categories get pretty much equal amount of data points. That's for how you have to try and create your data decision tree. At every point, your impurity has to be reduced. And this impurity in the decision trees is called the Gini impurity. You can read more about it in the link that I've provided. I will be providing it again. I will provide it in the resources as well. These are some of the applications that you can use. But there's also it is pretty obvious now that I've given you the reason as to why decision trees can be like inadequate. It's possible that there's a lot of like there's a lot of chance that your decision tree might not be effective. You might get if you're not able to reduce your impurity well enough, you might get pretty wrong answers, right? So there is a solution to this, and that is your random forest. So as the name suggests, it's like a cluster, a mixture of trees. In this case, decision trees. So here, what happens is that suppose you have a huge data set. What you do is that you pick out just some attributes from that data set or some data points from that data set very randomly. It's like a completely randomized version of your actual data set. So you just pick up a sample of it and put it into one decision tree. Then you pick up another sample and put it into another decision tree. And that way you do it with multiple decision trees. And when I say multiple, I don't mean 10 or 20, I mean ideally 100 data sets, 100 decision trees. So you just want to do it with as many as you can. And in this case, bootstrap data set is the data set that I'm talking about, where you take out a random sample and you put it into one decision tree. That's your bootstrap data set. Now, when you have hundreds of these decision trees, each of the decision tree will give you a different class. So as I mentioned, when you use decision tree, at the end you get a specific class. Like your data point is put into one class. That's the whole point of using a decision tree. So what you do is at every decision tree, you get one specific data point. Then you look at all of these decision trees and come up and find the the majority. Like say out of the 100 decision trees that you have, say 80 have said class A and 20 have said class B. So clearly 80 class A would be your final class depending on the random forest. Now that's called bagging. When you're taking the majority of all of your results of all the decision trees and giving one class to it. So that's the point. That's how random forest works. So you bootstrap your data and then you bag it and come up with one final class. This is like the solution of your decision trees. Now coming to K-means clustering. This is your unsupervised learning. So I'll tell you how this works. So you choose a random K. In this case, your K is the number of clusters that you want. And what the model does is that it picks out 3 very random points. Now the points can probably just be 3 of these points right here, or it can be any random 3 points. That's the first step. Then what the model does is that it tries to pick up closest points to those 3 points that I've picked up. So for example, if you take this point, it's closer to this point. So it's going to get into this cluster. And if you look at probably this point, it's closest to this one. So it goes into this points cluster. So that way, depending on whatever is closest to whichever point, it gets clustered. And then there's something called a variance check that is done. So what happens is that the 3 final clusters that are found, you find the difference between the centroid of that cluster and probably the farthest point of that cluster. And that value is tried to be like, it has to be minimized. You have to have the minimum variance to get the proper to get your proper clusters. And to do this, you get multiple like this whole process is iterated multiple times. You choose different you choose random points a lot of times and finally receive the best set of clusters. This is your unsupervised learning that I wanted to cover. Before this, I also had a question that I wanted to ask you people about random forests. So now that we're bootstrapping this data set, as I said, we're taking out random values and putting them into one decision tree and not really considering the rest, there's a high chance that around 1/3 of your points kind of get left out. You don't really use you. It can happen that there's high probability all of your points are not used in all of these decision trees. So my question to you guys is, how can those points be used and how are they usually used in random forest? It'd be great if you could probably put it out in the chat or research more about it. That would be great. That's one question I had. These are some of the algorithms that I wanted to cover, but there are a lot more. There's a lot many more algorithms that are out there that you can start off learning machine learning with. But these are some things that are used are used a lot, and they're essentially very important. So these are some of them that I wanted to cover. And now I have 2 demos that I want to show you guys. So the first one that I have here is a simple linear regression, a multiple linear regression model that I want to talk to you about. This is the Boston data set. It's in the sklearn libraries itself, and you can go and check it out. This is all the features. These are the features that are present in the data set, and these are the target values. So in this data set, what we're doing is we're trying to find the median value of owner-occupied homes or in a specific area, and we're taking into consideration crime rate and age and tax and lower status of population and all of that. And we're trying to figure out how the best fit line would be and how, given a new set of points, what would be your final cost, right? Now, what I'm going to do is I'm going to take one example. Let's just consider the lower status of population. These are the scatter plots of wherein I have put every single feature with the final output that we want to see. So here we see that crime rate depends this way, like the median value depends this way on crime rate and stuff like that. Let's just take an example, as I said, of lowest status of population. It'll be easier to understand. So over here, we clearly see that there's an inverse relationship between the two, right? So ideally, what we'll have to see in the end is that the coefficient that we get for this specific value, that is L stat, the final coefficient that we get for this should be negative because it's clearly inversely proportional, and we see it here. Let's see what we get after applying this thing. And this is your heat map. It just gives you the correlation between any 2 points. If they're similar, then one of them can just be ignored. These are just some histograms of each of the attributes. Now, we've taken the last value to be inversely proportional. And now, after applying the linear regression model, we see that the final value is negative. So it shows that because your LSTAT value was inversely proportional to your median value of the cost, you've got a negative value. That's an example of how linear regression works. And we get an intercept. And this is this is only one of the points. I've only taken crime rate and plotted the points. But when you take points of all the, since it would become too confusing, I didn't take all of the points. But when we put in all values of like LSTAT and everything together, we realize that this is the minimum, minimum best fit line. Now coming to KNNs. So I've used different values of K and shown you the result that we get while changing the values of K. To say, when I've taken the value of K as 1, so when you take a value as small as 1, it's very highly likely that that 1 point could just be an arbitrary point and you won't really get the answer. So if you look at this, you see that the graph is extremely overfitted and it's not really smooth. So it's clearly a wrong graph. But as in when you start increasing the value of K, you get better and better. But there's also a chance that if you highly increase it, that you might not find that much of a change. So you trying to find the value of K is extremely important, and that you can do with the help of cross-validation, or there's a lot of research that goes behind it as well. So with that, I have come to the end of my presentation. And in case any of you have any sort of questions, you can reach out to me at any time, and I'll be very happy to answer your questions. Also, all the links I will be providing on the resources page soon. Make sure to check that out.
Yeah. Thank you so much for your presentation, Ananya. So one more question. If I want to use ML to build systems to pick up abnormal blood test results, would that be possible?
I didn't get the question. I'm sorry.
Is it possible to use ML to find out abnormal blood test results?
Yeah, it is possible to use ML for that. Say like anomaly detection can be used. That's a form of unsupervised learning. So, yeah.
So that's another example of unsupervised learning in this case.
Yeah.
So is it true that like you need to to actually use those models? You need to learn scikit-learn, right? Python scikit-learn. That's the best way to start exploring all different models.
Yeah.
So one more question, like why do we have many different models for the same task? For example, for classification, wouldn't it be better just to always use, for example, a very powerful neural network model and forget about the rest?
So neural network is like something that's built on machine learning, right? Sometimes you might not have very complex models, very complex data sets, and you can just use a simple machine learning algorithm with lesser, and it would probably use lesser GPU as well to just give your output, and also might yeah. So yeah.
Yeah, I think it's also very important to mention the concept of overfitting. If you have a very powerful model but you don't have enough data, then the model can learn exactly like with its train on your data, it would learn the patterns in your data, but it will not generalize well. So you should always balance between complexity of the model and the amount of data you have. So, for example, for regression model, regression is like the simplest one. When you are building essentially a straight line through a number of points, you need like a few points, like 5, 6, and you can already build the straight line. But if you want like more complex behavior, more complex model, then you need more points and more dots. Okay. Thank you again so much for your presentation. We hope to see you again in our next conference. And now let's play a short commercial before our next talk.